Okay, welcome back to the next session, the first regular session of today. We have 3 talks in Macs and AEs. The first one is revisiting leakage resilient Macs and succinctly committing AEDs, more applications of pseudo-random injections, and the talk will be given by Mustafa Kairala. So go ahead.
Thank you for the introduction. So I will be talking about this topic, and if the title seems a bit scary, you shouldn't worry because in reality it's not this scary. So first, I want to mention some of the notions that will be relevant to this talk. First, obviously, pseudo-random injection. I will talk about that next. We also need to remember collision resistance. So we have different types of collision resistance. Hash functions, which is a standard collision resistance, but we also have collision resistance for Macs and the encryption functions. And in those cases, basically, you just consider all the inputs. It's similar to a hash function, but you consider all the inputs to be controlled by the adversary, including the secret key. We also will talk about unforgeability, which is a standard notion for Macs, unpredictability of 2 equal block ciphers, AED, and ciphertext integrity with leakage. And one of the main topics would be succinct commitment. So first, to recap, what is commitment in the CMT4 notion, which is the strongest commitment notion for AED. Basically, you have to generate 2 sets of inputs with secret key, nonce, associated data, and message, such that when you encrypt both sets of inputs, they have to lead to the same ciphertext. And this has practical applications, for example, in messaging apps where some malicious users can try to generate one ciphertext that is decrypted to 2 different messages. And I think there was a talk on the first day and later today that will show that in most cases, the security you get for this type of security notion is half the tag size. So the most obvious attack is the adversary will try to find a collision on the tag. And this is an offline attack because he can control the secret key. And then with up to half the tag size, you get security, but you cannot easily get security beyond that. Then in Crypto 2024, there was the notion of succinct commitment, which introduced by Pilari and Huang, which basically says that a scheme is succinctly committing if it has security beyond half the tag size. So what is a pseudo-random injection? I will not first give the technical details. I want to give some intuition what it is. So for example, imagine you have an encryption scheme where you are trying to hide messages inside these balls. And if the encryption scheme is a permutation, then you would expect that every ball has some secret message inside. But if your encryption scheme is an injection, then actually only a very few number of balls will have stuff inside and most of the balls will be empty. And this means that the adversary can try to check what's inside the balls, but they can also try to open random balls, and very likely these balls will be empty. And if we have that, then the scheme will be unpredictable. So he cannot know which balls will have message inside them without opening them. So this is the interface for a pseudo-random injection. We have key and tweak, which select the function. And then we have a plain text and the ciphertext. And the space for the plain text is smaller than the place for the ciphertext. And when we try to decrypt, we choose the ciphertext, we decrypt it. We may get a plain text if it's a valid ciphertext, but we can also get a rejection. So it's kind of similar to a Mac or a AED, but on a very small space. So we can actually use this as a Mac. So for example, we will define our message space as the combination of the tweak and the plain text. We encrypt that with the pseudo-random injection, and the ciphertext becomes the tag. And we can try to verify as well. So we can try to decrypt and see if the ciphertext is valid or not. We can add one extra thing is that we don't just look at the rejection of the PRI, but we can also look if it's valid, whether the plain text given by the adversary is correct or not. And this adds an extra check. And we can have some trade-offs. So for example, in terms of implementation, we can only look at the rejection from the PRI, which gives higher probability of forgery, or we can look at both. and we can have different assumptions for the security of both the equality check and the PRI. So to model this, theoretically, it's actually not very straightforward. So if you are familiar with lazy sampling in provable security, it's very simple for random functions or random permutations. But for random injections, it's actually complicated because we need to take care of invalid ciphertexts, and the probability of invalid ciphertext changes over the course of the attack. So like the more invalid ciphertext you get, the higher probability that you will get a valid one, and vice versa. And this means we have to have a dynamic random sampling over here at line 14, which tells you, like, keeps track of how many valid and invalid ciphertexts you have so far and adjusts the probability. And this model was actually introduced in the context of the analysis of the synthetic IV scheme many years ago. And recently, I used it also to show the security of short tags in AAD. And now it's for Macs. So we need certain properties for these PRIs. One of them is collision resistance. So basically, we can view the PRI as a compression function over all the inputs, including the key, tweak, and plaintext. And we can say, can the adversary find two sets of inputs that give the same ciphertext? And to do this, we have to define some bad events. So first, during the attack, the adversary will try to query the PRI. And if he can find two queries that give the same ciphertext, that will lead to a collision. But here it's different from a normal compression function because we also have an inverse function. So the adversary can try to inverse the PRI. And if he gets a valid ciphertext, then that can also lead to a collision. So he generates one ciphertext and then tries to invert it. And this leads to a slightly worse security bound compared to a normal compression function. So we have the first term, which is the normal security bound for collision resistance, which is the birthday bound. But we have the second term, and here N and M are related to the sizes of the plaintext and the ciphertext space. And in this analysis, the key and the tweak can be of any size. The security depends on the sizes of the plaintext and the ciphertext. And of course, like if the plaintext space is too big, close to N, then the scheme is not really secure. So we need the plaintext space to be much smaller than the ciphertext space. And even then, it's slightly worse than the normal collision resistance. So now another property we want for these PRIs is unforgeability. So as I said, we will use this as a small input length MAC. So we have the message will be split among the tweak input and the message input. And then during forgery, we will decrypt the ciphertext. If it is valid, then we will check the equality. And imagine if we don't care about checking the equality during forgery, then the probability will be actually similar to this second bad event. So it will be similar to this term, just with a different constant. So basically just the probability that during sampling we get a valid plaintext. Now, when we add the equality check, this adds an extra requirement that the adversary has to also not just guess a valid plaintext, it has to guess the exact value. So just a reminder, for unforgeability, we don't need the tag to be pseudo-random. So we just need it to be unpredictable. And we can consider the PRI also as a PRF, so we can consider the tag to be pseudo-random, but the bound will be slightly worse because of that. The PRI is secure, is around this value, and we can show that the probability of guessing the exact value is around this value. And then when we do the overall bound, it will look something like this. But we can have different assumptions here. So for example, here we are assuming that everything is leak-free in this previous bound. We don't have any leakage to consider. But imagine if we only have the PRI as leak-free. And leak-free doesn't necessarily mean black box, but like heavily protected primitive. But then imagine if the equality check is only leakage resilience, so it leaks some information. So then we have, instead of 1/2 to the M, we have some term that has to be determined from the equality check implementation and has to be tested. And then the security drops a bit. And you can say, okay, we lose security here So why not just do a normal MAC and do a leakage resilient equality check? What I wanted here is that I wanted to still have some security even if the equality check fails. So even if we consider that this block is completely insecure, we still have some resistance from the PRI itself. So the security it's not completely lost, but it just degrades a little. So as I said, this was assuming leak-free primitive. But in practice, this model has been criticized, and it's not very easy to verify that the primitive is still pseudo-random when it's leak-free. So there was a model that was proposed in AsiaCrypt 2021 called unpredictability with leakage. And it was proposed mainly for tweakable block ciphers. So the assumption is that even if you have leakage, the adversary cannot predict a point which includes plain text, ciphertext, and tweak that have not been seen before. And we can use this model here as well. Instead of complete unpredictability, we will have a model that says the adversary cannot generate a valid ciphertext even with leakage. However, there was a slight problem with this. So just to give a reminder for their proposal, they had a tweakable block cipher over here, and they give it 0 input. And if you consider this is actually a PRI, but the plain text space is just one value. And then for arbitrary length messages, they hash the message M, and then use the hash value as a tweak for the PRI. And the first inequality here is that what they prove for the unforgeability of this scheme using this unpredictability with leakage model. So basically, they say that as long as the hash function is collision resistant and the tweakable block cipher is unpredictable, we get this bound. Now, this bound, because they are not assuming any pseudo-randomness of the tweakable block cipher, so for every time they are doing forgery, they have to invoke this bound in a hybrid argument, and you get this product between QD and unpredictability. And in the paper, they claimed that this is actually less than, so the second inequality. And unfortunately, this turns out not to be true, because, sorry, if you have here this product, you can imagine that every time here you have the brute force complexity for unpredictability, and it's multiplied by QD. So it's actually much higher than this. But this, to me, is a problem with the model itself. So even when we apply it to this new version with PRIs, so now we change, with the hash function part is the same, but we change the tweakable block cipher to PRI. And we try to use this model, we get something similar to what they get. But when you look at the leak-free models, the bound for the leak-free models is much better. So to me, this is a problem with the unpredictability model, which does not assume pseudo-randomness. It's not a problem of the security of the scheme itself. So next topic I would like to talk about is how to use this primitive in succinctly committing AED. So the first scheme I will mention is a misuse-resistant AE scheme. So we have here a hash function that takes part of the message. So now we will split the message into two parts, one small up to m bit and one arbitrary length. The arbitrary length part we will hash with the nonce and the associated data using a collision resistance hash function. And then we will apply the pseudo-random injection on the part that's m bit. If the message is less than m bit, then this first part is not needed, the hash function. We just have a hash of n and a, or an empty string, and we use that as a tweak. Then this output of this PRI, we will use as an IV for a stream cipher, and we will also use as a tag. And for the encryption part, the stream cipher part, we will only use m prime, which is without the last m bits. During decryption, we have the tag. We will generate m prime first, and then we will do the MAC. And the MAC will give us back m star, because the F part will be done in inverse. And you can see that this is a combination between the SIV paradigm and the encoded and encipher paradigm, because the PRI is basically like an encoded and encipher scheme, but for very small lengths. And we can show that this has security for commitment up to half the text size. extension. So the security is more than half the ciphertext extension. Scheme. So we actually need the tag to be indistinguishable from random. So in the security bounds in the paper, you will see that the security bounds for privacy are slightly worse than integrity because of this. And this is why we need the nonce. So if it was not for that, we could have removed the nonce. Another scheme, but this is more like a high-level scheme in the paper called succinctly committing online AAD. And this is actually related to a different scheme that will be in one of the talks later in the day, where we split the scheme into two parts. One is an encryption function. This encryption function takes key, nonce, associated data, and again, an arbitrary length plain text M prime, and generates a ciphertext, but it also generates a V. And this value here is like a hashing of all this input, does not need to be pseudo-random, just needs to be collision resistant. Then we do the same thing. We apply the PRI on the last M bits of the message, and we get the tag. And this actually covers a wide class of schemes. So it covers, like, if the PRI is replaced by a normal finalization function, it covers schemes like ASCON or TEDT, all these leakage resilient schemes. So this can be seen as a way not to transform a scheme, but to change it slightly to get better commitment. And we can show that this is secure for CMT4 security. It's also secure when the encryption function has leakage, except for very small part, but the PRI is protected against leakage. And in the paper, we also show that it ensures privacy. But for privacy, because this is kind of like a high-level description of the scheme, we need a random oracle assumption for this encryption function. And I think this is like a good way to use the random oracle assumption, because we are not defining a concrete scheme. We are just giving like an intuition that this scheme is secure. So one last thing to discuss is, I talked a lot about these PRIs, but how to actually build them in practice. So one obvious way to build them is, as I said, using the encode then in cipher framework. So you just take a tweakable block cipher and you limit the plain text to part of the input and you pad it with some padding. And this can be done with ad hoc TBCs like Skinny, for example. But the problem is they have small size, so for commitment, they don't have good security. It can also be done with provable designs from block ciphers or from tweakable block ciphers. So one such design was the HTM design in Crypto 2024. But it's like it has some subtleties with the security bound, so needs to be careful when using it. I think this same design can also be done from permutations, using truncated permutations for the compression function. And I think it, like, for future, it will be very useful if we have a 200 to 256-bit tweakable block cipher, which currently we don't have a design that's up to this size that's actually accepted. Thanks. And
Okay, thank you. Any questions? So I definitely had one question, well, multiple actually, but one of them is you make this PRI, for instance, you can take a tweakable block cipher.
Yeah.
But if you then go to SCOEE, for instance, I mean, it's a quite big tag. So is it really added value to take a PRI there? Or what?
So the tag here is, I mean, it's basically n bit, but n, like if n is 128 bit and you say you take m star to be 64 bit,
Yes.
then you get security 66 tweakable block cipher.
Yes, yes, okay, but and mostly of the applications that you have, the PRI would typically be a tweakable block cipher, right?
Yes.
Then it works. Yes, yes. But is there any applications where a tweakable block cipher wouldn't really do it, and you really need like a bigger thing than like encode and cipher?
Well, the problem again is the block size. So because the commitment is a offline attack. So,
Yes, yes. Okay, any other question? If not, yes, Kazu.
Okay, so yeah, thanks for the talk. So the target about the committing security is the CMT4, as you said. That I'm wondering, is there any gain for the weaker security notion? I mean, the key committing, the CMT1 one. So it is a PRI gives it some advantage.
Think because, for example, if we take this scheme, so there is a detail in the paper that I didn't really mention, that we have these independent keys for the PRI and the stream cipher, but we don't have a key for the hash function, so the hash function is keyless. But actually, you need those keys for the commitment to work to be dependent, KF and KG. So you generate them from a master key using some collision resistant pseudorandom generator. And I think if you only care about CMT1, I didn't really study it in full because I focused on the strongest one, but I think it will work also here.
Yeah, thanks.
Okay, let's thank the speaker again.